Here's the second of our revision lessons, and this time it is on work done, energy and power. Now this is a very equation-heavy part of the unit, so we're just going to have to tackle this slowly and make sure we've got everything, make sure we can deal with all those equations. Right, okay, first we're going to start with work done. Okay, this is quite a simple equation. It says work done is equal to the force times by the distance covered. It's usually measured in joules. The force is measured in newtons and the distance is measured in meters. Now, there's a little subtlety to the distance thing because it's, and I'll explain through a diagram. Here we go. Let's imagine I have a block, and this block weighs, not mass, weighs 100 newtons. And let's imagine I try and lift that block 1.5 meters off the ground. Okay, that's my first example. I'm going to lift the block up off the ground. The second example is I'm going to push the block a distance of 2 meters along the ground. Okay, now the distance, of course, so we've got two problems here. Lifting, one problem, pushing, two problems. Now, for the first one, the lifting, well, that seems straightforward. Work done is force times distance. So therefore the force, well, what you need to consider here is weight acts downwards. So the distance in the direction of the force is 1.5 meters. So I have 100 times 1.5, give me 150 joules of energy. Okay. Now when it comes to pushing along, I've got the distance of 2 meters, but when I'm pushing it, I'm not going to consider this force here, the 100 newtons, because it's not in the same direction as the motion. I'll have to put in another bit of information that says I'm going to push it with 20 newtons of force. Let's say it's 20, that's how much it takes to push it against the friction as it sits on this surface. So in the second instance, the work done in pushing is going to be equal to force times the distance again, but this time it's 20 newtons times 2, which gives us 40 joules worth of energy. So it's important to say here, distance in direction of the force. That's the little caveat that's important in that instance. Okay, now work done is a bit of an odd idea to sort of get your head around, or it's an odd term to get your head around. But essentially what work done means is that whenever there's an energy change, whatever has caused that energy change is doing work. So let's talk about, a lift, and as it goes up, you've got a machine that's a machine that's rotating to lift the lift up. We know that obviously the people that are standing in this lift are gaining gravitational potential energy because they're going up. So however much gravitational potential energy they gain is the same as the work done by the machine, because the machine is causing that energy change to happen. Let's imagine, I think walking is the, things going up and down is the easiest thing, but let's imagine you're walking up to the top of the diving board. There's someone at the top of the diving board, and they've walked up a set of stairs. The GPE that they've gained getting up to the top of those stairs is the same as the work done by their body. So whenever there's a change in energy, the change, whatever's caused the change, has done work. So that's what you need to bear in mind. Okay then, let's just draw the triangle. Work done, it's force times distance. And let me give you an example, and you can give it a go. Okay, I've got a block, and I'm going to push it along the ground, and it's 50 newtons to push it, and I want to cover 10 meters. What's the work done? Okay, press pause and have a go. And then I'll go through the solution right now. Okay then, so the work done, it's very straightforward, it's force times distance. So therefore we have 50 newtons, so that would be 50 times 10, giving us 500 joules. Nice and straightforward. Okay, how about this one then? Problem number 2. I have a block. I want to push it, let's say I have pushed it 20 meters, and the work done needed to push it 20 meters was 4,000 joules of energy. What was the force required to push it along that distance? Okay, once again, hit pause, give it a go, but here is the solution. Okay then, I'm looking for the force, so if I go to the equation here, cover up force, it's work done divided by distance. So therefore the force is work done divided by the distance. So that means 4,000 divided by 20, giving me 20 newtons of force. Okay, so hopefully work done is fairly straightforward. Right, the next one we're coming on to is gravitational potential energy. Okay, there's 2 ways to consider this. You could first of all say to yourself, the gravitational potential energy is obviously what happens when you're moving something against gravity. And you move this certain height, and there's a weight to the object. So very much like work done, you can say the gravitational potential energy something's gained is the weight times by the height it's moved. In other words, a work done against the gravity, a force times a distance. Okay, great, but we did in the first revision session, we knew what the weight was. The weight is the same as the mass times the gravitational field strength. So really the GP could be rewritten as mgh, it's the mass, times the gravitational field strength times the height. Of course, G on Earth is 10 newtons for every kilogram. So let's look at an example. It's very straightforward, and in actual fact what we could write is we could write a triangle here, which we have GPE, and I'm going to put mg together and h. Okay, so though the triangles are only good for 3 subjects in an equation, this is not too bad if you consider that to be the weight. Right, let's go back to that example of the diving board. So somebody's standing on the diving board. They've obviously walked to the top, the load of stairs. This is an 8-meter diving board. How much GPE has that person gained in, I'll put some water there, otherwise it could be a dangerous jump, in walking from the bottom to the top? Okay, if you think you know the answer, hit pause, otherwise I'll go through the solution right now. Okay, so GPE gained. It's going to be mgh. We know the mass. Oh, sorry, I should have said the mass. Okay, let's go for a 70 kilogram person. Apologies there if you did hit pause and got a bit confused. Okay, 70 times 10 times the height of 8 meters. And that brings us to 5,600 joules. Nice and straightforward. What else? I'm just trying to think of another example where we might use GP. I mean, it is that straightforward. You, of course, please bear in mind the height and place it in meters. Please bear in mind the weight and put it in kilograms. This is for all of these equations. So let me give you another example of it. Let's say apple. This is an apple. Okay, and the apple I'm going to put on a shelf. It's 120 centimeters high, and it weighs it has a mass of 100 grams. Okay, what's the GPE gained in moving it up? And then you can say how much work needs to be done from me if I'm to lift it that distance. Okay then, hit pause again, give it a go. Otherwise, here are the answers. Okay, first of all, the GPE. Well, we've got our equation. But this time, we're going to have to bear in mind that we're looking at grams and centimetres. So my conversion is always into kilograms. You need to divide it by 1,000. Whatever you have, just divide it by 1,000. You know G is 10, of course. And the height, well, I've got 120 divided by 100, because that's the number of centimetres per metre. And that gives us a very, very simple solution of, well, that gives us 1, and that gives us 1.2, so 1.2 joules. It's a matter of gravitational potential energy it gains. So therefore, what's the work done by me if I'm lifting it up there? Well, it's the same as the energy gained. Remember we said work done is the amount of energy something needs to put into it if it's changed that amount of energy. Okay, brilliant. Right. Well, let's just do one more so you have another manipulation of this equation. Let's say that you've got a ski lift. It starts off here, it goes up a mountain and finishes somewhere up there. It gains a height of 1 kilometre. No, okay, it's crazy. 100 metres. It's a gondola. It covers a distance of, let's say, 1 kilometre. And I will tell you that the GPE gained is going to be, let's say, 1 million joules. Okay? What is the weight of the gondola? Okay, there's an example. It's quite a tricky example. Okay, and if you think you know the answer and you want to give it a go, hit pause. Give it a go. Otherwise, here comes the solution. Okay, right. So we need to, first of all, our equation, GPE is mgh, or actually, if we want WH, because we just want the weight of the gondola, we are interested to know the weight, so the rearrangement of the equation is GPE over H. Okay, my GPE is 1 million joules, and the height, now this is the important point, weight of the gondola is acting downwards. So therefore the only height we're interested in is the 100 metres. Not this length here, but just the 100 metres. And that should give us a weight of 10,000 newtons. Excellent. Okay, that's right. We're going to go to our one of the last topic areas, and that is kinetic energy. Okay, so very simply, let's just write down the equation. Kinetic energy is the same as half times the mass times the velocity squared. Once again, it's in joules, kilograms, meters per second. Obviously that will be squared as well, just to keep it consistent. It talks about movement energy, how much energy a moving object has. So let's have an example then. Let's have a car, another one of my terribly drawn cars. And let's imagine this car is moving at 10 meters per second. Oh, hold on, wait a minute. Let me just try and draw a triangle for you if I can. Once again, it's very hard when you don't have three terms. Kinetic energy is, we'll go for half m this side, and we'll do v squared on that side. Okay, those are our three terms. Okay, it's moving at 10 meters per second, and we've got a 500 kilogram car. What do you think its kinetic energy is? Once again, you can pause the video if you want, or we can just go through it straight away. The kinetic energy is going to be half mv squared. half times 500 times 10 squared, which should be a very simple equation, giving us 25,000 joules of energy. Brilliant. So, so it looks a bit odd to manipulate, a bit difficult, but actually it's a straightforward equation again, just talking about movement energy. Let me ask you one more thing. So, bullet. There you go, bullet. It's moving at 300 meters per second, just slightly under supersonic speed, and it's 10 grams. What's the kinetic energy of that bullet? Hit pause, give it a go, or here's the solution. Right, we've got a half mv squared again, but this time you have to make a conversion for the 10 grams. So once again, all I do is, if I'm converting from grams to kilograms, divided by 1,000, and the 300 meters per second is actually okay. I'm just going to plug into the calculator just to make sure I don't make any mistakes with this one, and I get 1.5 joules of energy. No, I don't. Hold on. 450 joules of energy coming out from that bullet, which is quite interesting actually. It's not very much because of that decrease in mass considerably. It's not very heavy. Okay, now with all of these examples, you're going to need to talk about how the energy transfers. How the energy moves from one form of energy to another. So let's give a few examples here. Let's first of all look at that person on the diving board, for instance. Has the steps, they walk up to the top, standing on the diving board, and well, let's use similar type of figures as we used before. Let's go for a 5-meter diving board, a 50-kilogram person, hopefully the sums will be made easy, and they jump off the diving board and they go into the water below. Okay, the first question is, how much gravitational potential energy do they gain by walking to the top? The second question is, how much kinetic energy do they have when they jump off just before they hit to the water? The final question is, what's the velocity do they enter the water with? So 3 parts. If you think you know what they are, hit pause. Otherwise, I should go through the solutions right now. Okay, then first of all, gravitational potential energy is going to equal mgh. We've done this bit before, this is straightforward. 50 times 10 times 5, and that gives us 2,500 joules. So that's a bit small, hope you can see that. Now, of course, when they jump off the board, the reason why they pick up speed is because they're changing gravitational potential energy into kinetic energy. So, assuming there's no friction, which we do in these instances, when they jump off, the loss of gravitational potential energy turns into the kinetic energy, gaining speed. So at the bottom here, what they've lost at the top, they've gained at the bottom. So very simply, it should be the same. And what's the velocity they're travelling at? Now this one's tricky. Take a look up here. If I cover up the velocity squared, it's kinetic energy divided by a half m. So the velocity squared is the kinetic energy divided by half m. So let's do that. 2,500 divided by a half times 50, giving us 100. We're not done there, that's velocity squared. So therefore velocity must be the square root of 100, which gives us 10 meters per second. So that's how fast they hit the water. Hit the water at 10 meters per second. Okay, we could have another couple of examples if you like of that. Let's look at a car travelling along a road. Another terrible car. It's looking even worse these days. And let's imagine it is travelling along. Well, let's say it's travelling along with a kinetic energy of 1 million joules. Okay, it's a 500 kilogram car again. And at that speed, what's the velocity? Okay, hit pause, give it a go, but here's the solution we're going to run through right now. Okay, as before, we say the velocity squared, look at the triangle, is going to equal the kinetic energy divided by half of the mass. So that's 1 million divided by half of 500. That gives us 4,000. 4,000. Nothing yet, no unit there yet, because the velocity is going to be the square root of 4,000, giving us 63.2 meters per second. Okay, I jumped at some figures there, that's incredibly fast. But there we go, let's just use that as an example. Okay, now let's say it puts on its brakes, and this car takes 100 meters to stop. So it's going at 63.2 meters per second, and then it's going to 0 meters per second. Okay, and what's causing it to do that? Well, the brakes, obviously. So we have lots of kinetic energy at this point, and at the end, what happens? Well, remember I talked about the transfer of energy. Where's all that kinetic energy gone to? Well, whatever's doing it is doing work. And I'd say that's done by the brakes. And obviously it's gone into heat in the brakes, interestingly, and then it's come to 0. It's stopped. So therefore, my question is, what is the force exerted by the brakes if it's managed to stop this car in 100 meters? And bear in mind that it started with 1 million joules, which related to 60 kilometers per hour. If you think you know how it's done, press pause, otherwise here comes the solution. Well, the kinetic energy, which is the 1 million joules, has turned into the work done, which is the force times the distance. Now we know the distance of 100 meters. We want to know the force. So the force is going to be the work done, or the kinetic energy divided by the distance, divided by the 100, which gives us 10,000 newtons is what the brakes exert. Pretty impressive. Right, here we come to the next bit, power. Next topic point, power. Power is very simply saying how quickly something converts energy in. In other words, the power measured in watts says how quickly that energy is being transferred from one place to another place. So for instance, a good example is running up some stairs. You've all done this as an experiment. Let's imagine it was 10 meters, and this person of 70 kilograms has run up those stairs. It's taken them 10 seconds to run up those stairs. How much power have they converted in running up those stairs? You think you know the answer? Hit pause, otherwise here comes the solution. The power is the energy divided by the time. The type of energy they're dealing with is gravitational potential energy divided by the time. The gravitational potential energy is mgh divided by the time, so therefore simply power is going to be 70 mass times g times h, 10, divided by, we said 10 seconds. 700 watts of power. So actually, once you've dealt with the energy conversions, and then you're asked about the power is very straightforward because you're just dividing it by the time available. So I think that's a straightforward one. And very finally, we're dealing with Sankey diagrams. A good example is, say, a light bulb giving off light. It's just a graphical representation of what's being usefully converted as opposed to what's being wasted. Okay, and it's drawn to scale. So this represents your input energy. This always represents the useful energy, the one bit going straight forward, and the wasted energy is that bit which comes off. These must be drawn to scale. So if, let's imagine, in this instance is the light bulb, I have 100 joules of electricity coming through this electrical circuit. I now know that 20 joules are given off as light. So therefore, this should be 100, this should be 20, and this should be 80 joules. And that's how it's drawn to scale. If you're given a graph, you draw that to scale. And I suppose that begs the question, what's the efficiency of these devices? Well, it's very simple. It's the useful energy divided by the total energy, often written as a percentage, so multiplied by 100. So in this case, the useful energy is 20, because that's all that's coming off as light, bear in mind, which is the top bit, divided by the total input, which is the 100, times by 100 gives me 20% as its useful output. So you just need to remember about the Sankey diagrams and how they're drawn. And of course, this equation of useful energies, it's very useful and linked very close to the Sankey diagram. Right, hope that helped. That's it. Second bit done.